Good evening, everyone, and thank you for joining us for the Smithsonian National Air and Space Museum's Exploring Space Lecture Series for 2023. I'm Ross Irwin, geologist and chair of the Museum Center for Earth and Planetary Studies, where we study the geologic processes that have shaped the planets and moons of the solar system. Science fiction gives us a vision of human life throughout the solar system and the galaxy, but few worlds are truly habitable for people. The 2023 Exploring Space Lecture Series examines the realities of living and working in space for long periods of time. This story begins with remote bases on Earth and then looks outward to the International Space Station, future bases on the Moon and Mars, and the challenges of life on more distant worlds. We also learn about the Earth as a habitable world. This lecture series is made possible by the generous support of Aerojet Rocketdyne and United Launch Alliance. Our distinguished guest speaker tonight is Dr. Julie Robinson, Deputy Director for Earth Science at NASA headquarters here in Washington, D.C. She supports the director in managing NASA's Earth Science portfolio, including research and applications, data access, technology, mission development, and operations. Dr. Robinson was the Chief Scientist and Manager for Science and Technology Utilization in NASA's Exploration Systems Mission Development Directorate from 2020 to 2022. In this role, she developed the strategy and plans for research in human spaceflight, including the International Space Station, commercial low Earth orbit, the Artemis return to the Moon, and future missions to Mars. In 2018, she served as Associate Director of NASA's Human Research Program, coordinating a research strategy for ISS and Artemis to reduce risks to crew and prepare for human missions to Mars. Previously, she served as Chief Scientist of the International Space Station Program at NASA Johnson Space Center. Her professional experience has included research activities in virology, analytical chemistry, genetics, statistics, animal behavior, field biology, earth science, and remote sensing. She has a BS in chemistry and a bachelor's in biology from Utah State University and a PhD from the University of Nevada at Reno. She's received numerous accolades for her scientific leadership and mentorship, including the NASA Outstanding Leadership Medal. After Dr. Robinson speaks, we'll have time for questions and answers. So if you're here in the room, there will be a microphone about the center of the room, or you can submit your questions online. Afterward, please visit the National Air and Space Museum's website for more information on the next two Exploring Space lectures for this season. I'm very grateful to our sponsors, Aerojet Rocketdyne and United Launch Alliance, for their support of this series, and thanks to all of you for joining us tonight to learn about life support, what the International Space Station teaches us about our changing Earth.
Well, thank you so much. It is such a pleasure to be with you tonight here in this beautiful reopened museum and this amazing planetarium as well. I know for the years that this space was not available to us, it really kind of hurt to not be able to see some of the amazing artifacts. And I've gotten a chance to look around this evening and see some of the new content and the new frameworks, and it's just amazing. So I know you must be as excited to be here as I am. And thanks in particular to Dr. Ross Irwin for the invitation to come and speak with you tonight, and the amazing staff that I've been interacting with. You know, when humans explore space, we reproduce the same systems, and we do them with engineering that nature and the Earth provides to us for free. And those systems, the life that support life, water, air, the surface, and the biology, are complex and amazing in their own way. In several decades of continuous presence that we've had on the International Space Station, we have learned surprising things about what it really takes to support humans living and working in space. At the same time, we have collected extraordinary data about that Earth and learned a variety of things that I'd like to share with you tonight. And really that connects my own life and my own career trajectory, where I've worked in both human spaceflight and inner science together. And so I'm hoping that as I connect these ideas together, you can leave today with a better understanding both of how, when we explore, we see the universe in a broader sense, but we also learn a lot more about ourselves and about our home planet. So there we go. On Christmas Eve of 1968, I was very small and not appreciating this event. 3 Apollo 8 astronauts, Frank Foreman, Jim Lovell, and Bill Anders, were the first humans to see this view of the Earth from space. This is what they saw, our home planet rising above the lunar surface, that barren wasteland, floating in the infinite blackness of space. And Lovell said, "The Earth looks like a great oasis compared to the great vastness of space." This photo was taken during a live telecast. The astronauts turned the camera around and framed the Earth. And this picture, called Earthrise, is probably one of the most significant photographs in the history of humankind, because in one event, it changed the way that we see ourselves and our relationship both to Earth and to the universe at large. It shows us the magnificence of our home planet. It also shows us its isolation and fragility. Go a little bit forward to another view of Earth that also has been changing the way that humanity sees itself. This view we often call the Big Blue Marble. It's the Earth as seen by the Apollo 17 crew. Astronaut Eugene Cernan, Commander Ron Evans, and the command module pilot, and of course, our favorite, the scientist astronaut Harrison Schmitt, geologist, was the lunar module pilot. And here they are traveling toward the moon. This was the first time that the orbital trajectories meant we could see the South Pole. And seeing that ice in the South Pole becomes incredibly important today as we look at the changes in the Earth that have happened since that time in the 1960s and early 1970s, and what changes have been seen during the space age itself. Well, by 1974, I was now much more engaged. And although I didn't know everything, I knew one thing, which is I watched the Big Blue Marble. And I hope there are some of you in this room who also watch Big Blue Marble on television, because that took this view, right, and it reframed it as that we are a small planet. We should have pen pals on other parts of this planet, and we could sing along with that television show and really start thinking about the Earth as a united place. And that is when I think I started realizing that studying the Earth and doing good things for the Earth was something that I wanted to do, and that was why I wanted to do that with science. And that's what led me through a series of career changes, sometimes in Earth science and sometimes in human spaceflight, but always the one ever-present thing has been the Earth. A lot of people think about the moon or Mars or the beautiful images from the Webb Space Telescope when they think of NASA. But the NASA Earth Science Division, where I am a leader today, is a $2 billion enterprise that focuses solely on understanding our planet. That mission is the mission to us right back here on Earth. And we have 26 missions orbiting the planet today. So in the animation, I think if it will run here shortly, you see some of those missions operating. This is actually what's going on with our 26 missions as they orbit the Earth today. They are collecting data and helping us understand the processes below them. And just to slow those down a bit, I think we need to advance on to the next slide. Oh my, now we jumped really far ahead. Let's go back. Okay, here's our Earth fleet. So here's the way you look at this chart. The middle of the chart closest to the Earth are the oldest satellites that we're operating at NASA. And as you spiral outward, those blue satellites are in extended operations. They go back to our oldest granddaddy satellite right now is Landsat 7, and then followed by Terra, Aqua, and Ara. And I don't know why that ran. Could we go back, please? Okay, that's way back. Can we go forward, please? I'm afraid to push the button. I'm afraid that it won't do what I want. Here we go. Now if we go one more forward. There we go, back to the swoosh start. The missions that are shown in green are just doing their operations. The missions in orange are those that we're planning or have just launched. Just last Friday, the TEMPO mission, a mission to study the continuous change in our air quality, launched from Kennedy Space Center just last Friday, and that is a Smithsonian operated and collaborative mission. And then the ones in yellow are the ones that are in our planning. And I'll talk a little bit about a few of these missions along the way. On that inside loop is an amazing thing, because when I started as chief scientist of the International Space Station, there were no plans to put any Earth remote sensing instruments on the space station. But in fact, we worked out opportunities for that. There were wonderful places to attach and operate instruments. And there you can see the 8 missions, 7 of them currently operating on the space station and 1 of them planned, that are observing the Earth from the ISS today. So the way that NASA Earth Science works, it's the only organization in the government in the United States that combines technology, figuring out new ways to make new measurements, building satellites, flying those missions, or building instruments and putting them on the space station, doing the research and analysis, building the data systems, the cloud computing, and the algorithms to understand that data, and then taking the information and giving it to people here on Earth that need that. Whether it is an international aid organization or NOAA to make improvements in their weather forecasting, we work with a variety of partners to get that information into the hands of people who can benefit from it in understanding our planet. And so I want to give you a sense of that view that we get as we look over the entire Earth. And so this is a compilation. What you see, if you look at the orange flares at the top of the screen, you see carbon dioxide being released in the northern climes, and then now you see those fires in the southern hemisphere, in the fire seasons, in Indonesia and Brazil and South America. In pink, you see nitrates. Those are from pollution from combustion coming out of industrial regions. And there now you see that yellow in the middle coming off of the Horn of Africa. That's dust spreading across the Earth. And then you can even see across the oceans that light blue sea salt being transported as an aerosol. And one of the things that we learn from a composite set of data like this is how the Earth is a system that's connected. So the idea of air quality rules in one nation respecting boundaries doesn't make any sense when you understand the way that the Earth actually works as an integrated system. And so I want to talk to you a little more about the Earth as a system and also about spaceflight as a system. So a simple way to break down the Earth, and you can find people who will tell you there are 9 systems or there are 7 systems. I decided to pick 5 because that's the number that they generally teach in 8th grade curricula, and it's a nice round number. And those systems are the atmosphere, the air, the biosphere, the living organisms, the lithosphere, the rocks and the hard surfaces, including volcanoes, the cryosphere, the frozen ice, and the hydrosphere, the water in the oceans and the lakes. And basically what we study in Earth system science is how those different systems interact with each other. What are the cycles and processes by which they interact with each other? And because this is a complex system, we keep finding surprises. Sometimes those surprises are good. Sometimes those surprises are alarming. And that is the beauty and the strength of what NASA has done in Earth system science over the last 30 years. Should mention also in the upper left, there's the radiation from the sun, because that's the energy source that drives this entire system. Well, what about in spacecraft? Because in a sense, the big blue marble is a really large spacecraft that is supporting we humans and all of the other organisms that live on Earth. Well, you can actually think of a spacecraft as providing all of those same systems. So here you go. See, now I talk about air recycling, the food that is needed for the organisms that live in that spacecraft. You need physical space, storage. You need the ability to cool and control temperature, and you need to recycle your air and your water. So in order for humans, and you need the sun to provide power, or else you're going to need nuclear power, one or the other. And so basically, the same things that we do in a spacecraft are actually reproducing and providing those core systems that are needed to support life. This is a really great diagram. This is the winning concept for the first closed-loop life support system for the Apollo spacesuit designs. This is from 1962. It was a winning design submitted by Hamilton Standard, which is now part of United Technologies. And if you notice here, the little boxes that are filled in with this systems diagram look surprisingly like the diagram I just showed you.
right? The water boiler, the contamination renewal, motors, batteries, valves so that you could circulate this, an emergency oxygen system to provide air. So this kind of shows you that those system components to support life are going to be the same in different situations. And in fact, a spacesuit can be considered to be the smallest spacecraft that humans know how to build. So on the left is the Apollo 11 spacesuit that's here in the Smithsonian collection. And we often think of the suit as sort of the fashion part. And so I put on the right the newly released photos of the Artemis suit with its black cover, which looks really cool. They won't leave that black cover on when they're on the surface of the moon. But you know, those spacesuits are essentially the same thing. They have a thermal cooling garment. They have the ability to circulate things. And the business end of the spacesuits is not the part that you see the pictures of. It's actually the backpack. And at NASA, because backpack doesn't sound very cool, we call it the PLIS, P-L-S-S. It stands for the Portable Life Support System. And so this picture here is the backpack for the Apollo spacesuit system. The little part on the top with the flags is the backup system, because oxygen is something that you don't have very much time to recover from if your PLIS quits working. And providing the system you need, that oxygen purge system is an extra tank of oxygen to get you back in the door gives you about 30 minutes of oxygen to get in. And so this is a spacecraft. It doesn't have propulsion, but this is providing all of those life support needs to that human who's living inside of it. It's keeping them cool, not letting them get too hot or too cold. It's providing the air system that they need. It's regulating the fluids that they might need to let out, and recycling and removing the condensation from their breaths so that it doesn't cause harm to them. So it is the smallest life support system, but it's a very temporary one. It can't be used for much more than about 6 to 7 hours at a time. Well, the International Space Station itself has another set of life support systems. And the amazing thing is that over the last 30 years, we've been able to use that space station to advance our technologies for how do we protect life in space. So when I first started at NASA, we were just thinking about sending crew members to live on the Mir space station with our Russian colleagues. And our spaceflight experience, we pretty much started to forget about Skylab, which was a couple of years of a space station. And we were really used to living and working in space for about 2 weeks on the space shuttle. And suddenly we needed to rethink the way that we did life support in space for 4 months, 6 months, and eventually year-long missions. And a big part of that has been improving the way that we do life support in space. So what is our life support system? It actually includes kind of 2 pieces. And the one piece is sort of the engineering side of how you keep all of those systems working, the fluids, the gases, and so forth. And so that includes our life support, also fire safety, because fires will use up your oxygen really fast, your logistics, and your environmental monitoring to make sure you know if you're going to suddenly get really dizzy or perhaps pass out. And then we also have a set of systems that I haven't been talking about as life support systems. We call those crew health and performance systems. Those are all the other things you need so that the weirdness of being in that space environment doesn't actually harm you along the way. And so those are things like our spacesuit physiology. What kind of exercise do we need to do rather than float around as the ultimate astronaut couch potato? How do we protect ourselves from radiation? What medical systems do we need if you can't get anything else from home along the way? And then what kind of food do you need to keep yourself healthy on a mission that could be many years long? So I want to just focus on a couple of things for this. And this is the overall system that we've been testing on the space station, advancing on the space station. This is what is being developed for our longer dwell times planned for the lunar surface in Artemis. And we have to have this perfected before we send people to Mars, or we will not be able to have them come back home. So in blue, one thing to pay attention to here is that life support, because it's those same systems that I just showed you on some of the previous charts. Atmosphere management, water management, waste management. And in our environmental monitoring, it is the same kinds of things that I showed you in that first graph of the Earth. Oxygen, carbon dioxide, nitrogen, humidity, trace chemicals, microbes, particles, and even the sound that can become harmful to people. And then down in the green on the lower right is the food and nutrition, because that's the simplified biota that's left. And of course, in a space station, you don't have room to grow all of the biota that would support our life support system here on Earth. So you try to figure out what's the minimum you can grow in the minimum space. So over 30 years on the International Space Station, we have made extraordinary advances in the way that we have shown and proven and understood the technologies for life support. And this is just a short history of oxygen generation advancement. So the Electron is the Russian system we started with. About 2001 is when this picture was taken. And these make oxygen by electrolysis, meaning taking water and breaking it into hydrogen and oxygen. Takes a lot of energy, and that system was not super reliable. So we Americans thought we would go and we would build a reliable system, the oxygen generation system. And here's a picture of that system in about 2012. It actually has not been overwhelmingly as reliable as we thought it should be, because in all of these systems we're dealing with microgravity, with fluids in pipes where bubbles come out. You've got two phases and the bubbles don't rise in microgravity like they would on Earth. So these systems turn out to be pretty challenging from an engineering perspective. And one of the most recent test racks is the advanced closed loop system that the European Space Agency launched in about 2018, and they're still checking out today. One of the things that we learned about life support systems in our urine recycling, in our water recycling system, is we made a horrible engineering mistake. We tested that system with urine collected from volunteers at the Marshall Space Flight Center. Well, they weren't shedding bone like early astronauts were before we had our exercise systems all worked out on the International Space Station. And when people are losing bone, they're freeing up calcium in their urine. So the calcium in that system actually caused it not to work very well. And we needed a lot more consumables, a lot more changes in filtration beds and things. If we had taken that early urine filtration system to Mars without having tested it on the space station, we would have ran out of consumables about halfway there. And so that's one of the reasons that we use the space station to test these systems and be sure that they're going to be reliable before we take them to a place where we can't evacuate and come home later. Well, I want to show you, this is a great diagram that Airbus is the aerospace contractor that produced the advanced closed loop system for the European Space Agency. And I wanted to show you this picture because on the right there in that cycle of reactions, you see, once again, a systems diagram where you've got air and carbon dioxide being removed by a scrubber, and then that carbon dioxide being passed to a Sabatier reaction that produces methane and water. And then that water can go into an electrolyzer and produce oxygen. And you try to get that system all closed so that you don't have to bring too much water from home and you don't have to use too much energy for it. And then the other thing our European colleagues have tried to do is attach a bioregenerative system to this to demonstrate that. Bioregen life support actually has not worked very well in spite of decades of testing. And I think it doesn't work well for the same reason that my attempt at having a pond in my backyard didn't work very well. It got more sun than I expected, and the fish didn't eat the amount of algae that I expected, and pretty soon I had something that looked like pea soup. And the problem that we have with bioregen life support is getting the wrong organisms or the wrong ecosystem balance. It's a similar problem that happened in the biosphere system. When we've tried to reproduce the complex set of biological interactions that maintain the Earth system, so far we haven't been very good at having things that are sustained for a long period of time. So chemistry is our friend in this system. But we do want crew members to have some things to eat. Even if a bioregen system might be based on algae or bacteria, we also need crew members to have some food that they grow themselves because vitamin A is not very stable in a radiation environment. And so this is Mizuna lettuce that the crew members grew on the space station and ate and demonstrated. At first, when I started, we wouldn't let the crew members eat it, and some of them did anyway, but they weren't supposed to tell us if they did, because we weren't sure that the microbes on it wouldn't make it dangerous for them, and we didn't want anyone getting sick. But eventually we got a sanitizing protocol, so they have to sanitize their lettuce before they eat it. And now crew members routinely grow radishes, zinnias, peas, and other things that they can eat on the International Space Station. But if you notice here, this is like growing food in your dorm room you're really not going to get the calories you need from this kind of food. And so building exploration food systems is still a huge challenge ahead of us as we think about missions to Mars. So what about the carbon dioxide system on the Earth? I showed you a carbon dioxide system for spaceflight. So in this diagram, wherever you see purple arrows, that is a sink, and wherever you see yellow arrows is a source where carbon dioxide is being released. So you can see there's some little rotting trees and rotting animals releasing carbon dioxide. Here you see the ocean serving as a sink and allowing carbon dioxide even to be released down into the lower sediments, but also it can bubble that carbon dioxide back out. And so understanding how the ocean is buffered with carbon dioxide and whether it's going to release or store it is really important. Then as humans start making changes, there you see some forest fires increasing the amount of carbon dioxide being released. And there you see a little train with some combustion, or a little car, also increasing the carbon dioxide. And that's the system that we have in our industrialized world, where humans have released enough carbon dioxide to start changing the nature of our system. And so if we could animate this image, this video will show you what a season looks like. So in this video, let's see, there we go. What you see is the levels of carbon dioxide in that bright orange that you can see through. And so right now, in the image in August, you see fires in Africa and in South America, in East Asia. And as we get further into September, we'll start seeing some changes happen that are seasonal changes. If you look in the northern hemisphere, it starts getting colder in October and November. Suddenly we see combustion releasing carbon dioxide as people burn fossil fuels for heat. And boom, look at all of that carbon dioxide spreading around the northern hemisphere where it's cold and there are the most people. And it becomes a denser and denser increase in carbon dioxide. And to look at it in January. So what I love about this diagram is it shows you how powerful, it should not have advanced there. That diagram shows you how powerful the, and we might have to go through it again, or we may have to skip it. The diagram would show you how powerful it is because what happens is that big orange cloud that forms across the winter, as we proceed into the spring, it goes away because the vegetation itself starts to incorporate that carbon dioxide into the bodies of the plants. And so the growing season has the ability between that and the ocean itself to remove carbon dioxide, and that's where the seasonal change happens. But of course, it's not enough. If we look at the overall changes in carbon dioxide across the last 50 years, we see a really large change or an increase. Another greenhouse gas that we can look at is methane. And greenhouse gases serve to trap heat in the atmosphere. So they function just like the glass in a greenhouse where sunlight can get through, but it can't always get out. Oh, look, they found us the end. We're just going to jump around on the Earth here together. Whatever picture they show, I have something great to say about it, so I promise you that. So here we are looking at methane, and methane is amazing as a greenhouse gas because it is very powerful. It's very potent as a greenhouse gas, but it also has a short duration. And so this has become a huge international target because it's a way that we could actually influence changes in our temperature in a short time frame. If we can cap methane, prevent methane from being released unnecessarily, then we can have an impact on the climate in the decade. So that is very doable, where carbon dioxide is a much longer dwelling part of the atmosphere, and it's harder to make immediate changes. So one of the things then that we see from all of these trapped greenhouse gases are changes in the temperature. And this is the classic chart from Ceres on our planetary heat uptake, looking over time as you get into the last 10 years, and we'll let them run that again. I think if we go back, please. So we'll just run it one more time so you can watch that temperature. It starts in 1883, and it moves forward to the present day. you could play that. I know it plays. There we go. So just watch. The oranges and reds are getting hotter and hotter than the monthly means of before. And so what you see is as we move into 2018, 2020, we are seeing the hottest observations of global temperatures in the historic record. And many of us have that experience. If you think about, my daughter's college in Chicago, they didn't have snow stay on the ground this winter at all. Like it would snow, they got a little bit of snow, a little pile somewhere, and then it melted back off. That's unthinkable. When I was a child, Chicago was just snowed in. And so we're seeing changes that are happening in our own experience, in our own lifetimes and days. There's a really great way that the Goddard Institute for Space Studies, working with us, represented this. So this is a calendar. As you go around the circle, that's a year. And if the line is blue, it's colder than the average. And as it turns white, it's at the average. And then as it starts turning pink, it's warmer than average. And so now we're seeing basically the time from the time of my grandparents to today. Here we come through the 1940s, haven't seen much pink yet. And all of a sudden, we start seeing pink showing up. As we get to the time when Julie started paying attention to the weather, we see more and more pink arising. And that spiral continues. Now we get into time that we're really remembering. We can think of our favorite rock bands. And look, the colors are all orange and red. Here we come into our current time. And when you see this in the press, that these are the warmest days on record, this is actually the data that shows that. And then what I love is they've turned this spiral so we can see it over time from 100 years ago at the bottom all the way up to today and see that extraordinary change in the temperature that's happened. Well, where does that heat go? It doesn't just go in the air. It goes into the oceans because water is the best sink that we have. It stores a lot of energy. And in this diagram or in this image, you see the ocean heat content increasing. And then you see how that heat actually drives kinetic energy, how it drives the motion of the currents. And here you can see some of the major currents, the loop currents, the Atlantic currents, and see that mixing that is occurring as that heat gets moved throughout the ocean. So then if we advance to the next chart, the next image, what does that mean for the ice? Well, here is a view of the poles over time, and you see that change happening where we have the seasonal change, but the amount of ice and the extent of that polar sea ice is much reduced compared to historic times. And then if we advance on to the next picture, then what we see driven by those dramatic changes in the way that heat is distributed around the world and the way that ice is reflecting heat away and the way that land is absorbing heat, then we see these huge changes in the system. In the ocean itself, cold fresh water is up high, the warmer salt water is down below, and we start seeing erosion of the ice masses that are interacting with the ocean. And then we start getting dramatic changes in sea ice, where we see that kind of a calving event happen, because before we see it on the surface, underneath, that entire ice structure has been eroded and minimized. And then if we go to the next image, so this is what we see from two of our missions, GRACE and GRACE Follow-On, which is able to make microscopic measurements of the differences in gravity as there's more or less land in different parts of the Earth, which is an astounding kind of a measurement to make on a global basis. And what you see in this animation is that record that's been collected. Where it turns orange is where the mass of ice has decreased over that time period. And you've got Greenland on the left, Antarctica on the right. The graph shows the actual numbers. Those really dark places are where there's been an extraordinary loss of ice mass, and you see them getting darker and darker as we head towards the measurements that we're taking right now from our GRACE and GRACE Follow-On missions. And if we go to the next, so then what does that mean? Well, melting of ice means that we've got significant changes in sea levels. And the sea level data is shown in the upper right here with the rate of change in millimeters per year. And then that leads to extraordinary impacts from high tides, from storm tides, even clear air or storm-free tides where we just get really high tides. And those things are causing all kinds of impacts across our coastal communities and around the world. But it's not just having too much water on the coast, it's also having other areas that become too dry, because as we start changing the way that energy flows around these systems that's driven by these changes in carbon, then we see impacts where areas dry up, lakes dry up, the Great Salt Lake you've heard drying up, and it's so dependent on the way and the pattern where the water falls and the pattern where the dryness occurs. And many of these, we can model them, and we spend an extraordinary amount of effort in doing good models, but in any system that's this complex, we are going to have things we don't understand. So we learn what we can from the models, and then we have to learn from the things that the models don't predict as well. Next chart. So one thing I think about a lot, because my grandfather was a farmer, is what does this mean for global food? And there are two images here. They're showing over time. These are projections. They're not a model, but they are, if we kept trying to grow the same thing in those places and the climate changes the way we think it will, what happens over time? And in the upper right, you see it getting very green as wheat yield projections get higher in the far northern hemisphere. Of course, where my grandparents farmed was in the desert Southwest, and there's no more wheat there at all. At the same time, you look at the maize yield projections. Now, maize is typically a hot weather crop, but it's growing in places where it's already at the level of its heat tolerance. And so we see projections that would have the corn crops collapsing across many parts of the world, including across the United States. And what's really alarming is if you look in tropical Africa, you see places where the wheat crop doesn't do any better and the corn crop would decline. And so what crops are going to be suitable for providing food in those areas? So these projections, they don't give us a prediction of the future, but they help us to understand what we need to be thinking about in terms of this Earth system and how the biota will support human life. Next chart. So on the International Space Station, as I mentioned, we have a number of instruments that are really taking cutting edge, new to science measurements of aspects of our Earth system. And I'm only going to talk about 3 of those today, but I wanted to give you some sense of how many of those instruments are pointing down at the Earth. And the amazing thing is, since they're all in one space station, they're all collecting data essentially simultaneously from the same place. And so the first of these I want to talk about is ecostress. So ecostress measures surface temperatures. And in the upper right hand of this picture, you can see an iPhone app that will let you, with a certain tool that will let you do a thermal image. And so you guys have seen this on Spy TV or on CSI, right, where they can look and see the print, the thermal print that a hand makes. Well, this is essentially using that same kind of technology, but looking at the thermal radiation coming off of urban heat islands. So this is an image of Las Vegas last June, and the streets down the strip, which you can see that angled street going right across, are 122 degrees in the middle of a heat wave. So much hotter than the area around them. And so this ecostress instrument is helping us to understand that, helping us to understand how evapotranspiration, the movement of water through crops, is affected by the temperature, and also even helping us to predict where wildfires might burst into sudden flame versus where the plants have enough water left in them that they may not be as vulnerable to sudden wildfires. Another instrument on the International Space Station that I really love is JEDI. So JEDI uses a technology called LIDAR. It's a laser being shot down at the Earth. And if you look in the upper right, that image of the trees shows you what a LIDAR does. So a LIDAR is shot down and then it bounces back to the source, and it can see that there are different edges or layers in that surface, and it can recognize those. What that signal looks like is in that kind of wavy diagram down the middle of the chart. And what it's showing you is a signal obtained from a California redwood, where we can then infer the height of the canopy and the amount of biomass in that tree. So that gives us an extraordinary way to make inventories of carbon storage in forests, because it's not just saying that's a forest because it's green. This is actually saying that is a forest with this kind of canopy and this kind of density. And that instrument is now being used to create a complete forest inventory of the world as it patiently waits for the International Space Station to help it collect data from all of the different sites that it passes over. And this is what a canopy height map from JEDI looks like. It's pretty amazing to see. You can see basically where the tallest trees are in the world on average. And that is the most complete canopy height data set to date. Here's biomass density, so that density of carbon that's stored in the bodies of trees all around the world. And this is really exciting to me because this is the biomass uncertainty. So as we try to get in a world where we have political and economic systems to track carbon dioxide and how much has actually gone back into planting trees. If you want to plant a tree to help save the world, this is what you want to see. You want to understand where the uncertainty is and how accurately we actually understand that to make sure that we have systems that are economically viable and that can't be cheated against, where we can actually take really good measurements and understand the biota. And my final example is EMIT. This instrument just went up last year, and it was originally designed to look at dust being transported. Back to that first image I showed you at the very beginning where the yellow clouds of dust were moving across the Atlantic Ocean from Africa. That was what this mission was designed to do. But it's an imaging spectrometer. It looks at all of the colors it sees in very fine detail. And it turns out we can also develop algorithms that help that instrument see methane. And what you see here is a methane point source that was detected by EMIT. We've put out 5,000 data cubes on these, and people all over the world have gone out and capped those sources of methane. If you're in West Texas in the Permian Basin and you've got a pipeline, a natural gas pipeline, and EMIT goes and sees this coming out of your natural gas pipeline, that is money leaking out of that pipeline. And so the first thing you want to do is go cap that problem. And so this offers an extraordinary ability for remote sensing data to create actionable information that people can use. So the Earth System Observatory is our next step in taking the technologies like I showed you on the space station and making sure that those are in a global observatory where all the data is accessible. And so you can see the measurements we're talking about here are those same 5 Earth systems. In fact, maybe now you're thinking, maybe that's why she's into 5s. The atmosphere, the mass of the land, the lithosphere, looking at surface deformation and change, the biology and geology, and actually shown here, but we already have some great missions, both SWAT, which just launched, and PACE coming up next year are the missions that look at the oceans and the inland waters. And so these missions all together help us to really understand the state of the Earth system today. And then in addition, we have targeted systems that we'll be selecting to look at some of the special needs we know of, like ecosystem structure and snow depth, distinguishing snow from ice, understanding the ocean surface winds, and detecting greenhouse gases. So what we've developed at NASA is an Earth action strategy. We have the Earth system observations we've been making for 30 years, and we are advancing those to the next generation. And then we take those and we understand, we do the research and we do the modeling, but the key is to take that information and develop it into things that people can use to make better decisions about their daily lives, about managing their communities and managing their countries. And then we also are working on our new Earth Information Center so that everybody can see the kinds of data that I showed you today and even be able to control it and look at what it means for their local communities.
For more than 50 years, NASA has been collecting and providing data on Earth's land, water, ice, and atmosphere. Now, a new era of Earth science has begun. Together with international partners, NASA will launch the SWAT mission to provide the first ever global survey of Earth's surface water, the oceans, lakes, and rivers that affect all of us. But we also need to understand our planet as a complex whole, That's why NASA will launch a fleet of state-of-the-art satellites forming the Earth System Observatory, which will create a comprehensive 4D view of Earth, from bedrock to atmosphere like never before. The Earth System Observatory will arm us with crucial data to help us address climate change and protect our communities. But how do we get this critical information to the people who need it? Introducing the Earth Information Center. NASA, working with our federal partners, will equip decision makers with the information they need to mitigate, adapt, and respond to climate change. We will create a greenhouse gas monitoring system and make data about our changing planet accessible to those who need it most. New satellites observing in the sky, and an information center here on Earth, protecting our planet for the next generation.
So if we go to the last chart, I want to tie this back to where I started, which is that the one thing we learn as we go out into space is how precious and difficult it is to sustain human life. This is the view from Orion on Artemis 1. It's not occupied by humans yet. We're still making sure that it's going to be safe. But that is the view looking back at the Earth from this new generation of missions. So even as we learn what it takes to support human life in space, at NASA, we also look back at Earth and use those same resources and that same ingenuity to study the Earth. And thank you so much for your attention, and I really look forward to taking some extra questions. Thank you.
Well, thank you very much for that wonderful presentation, tying together life support on the International Space Station to the perspective that it gives us on Earth as a habitable world. We have a number of questions from our online audience, and I'm sure we'll have some here from the room as well. If any of you have questions from our guests here in the room, there's a microphone there at about the center of the room. The first question we'll take is online. Have you examined Navy submarines as a mission analog, especially for life support systems?
Yes, we have. Our human research program has worked with the Navy and especially studied submariners on extended tours underwater, and that is a really interesting analog for human spaceflight. The biggest difference is the population. So submariners are young, and they're working in shifts. There's a fairly large number of them in that ship. And so we wind up seeing them behave differently and have different psychological responses than our astronauts, where you have 4 or 6 of them, and they're more in their 40s, they're a little more mature. So it's interesting both what we can learn and what we can't learn from an analog like that.
Mm-hmm. How does the human body change as you transition from being on Earth to being on the International Space Station?
Yeah, so as you leave Earth orbit, and you get to the point where there's no gravity, and those of you who watched, the Orion launch saw the little Snoopy start floating when we leave that gravity environment. And what happens in your body is many things in our body are adapted. All those fluids are adapted for having gravity. So the fluids start shifting up into your head. And when we see astronauts fly that we know, we call that puffy face and chicken legs, because they don't look like the people that we knew as well. If you see their legs, they look really skinny, and if you see their faces, they look kind of round. And so those fluid shifts occur early in the mission. Then over time, the body actually gets rid of some of that fluid and decreases its blood volume. And all of those processes going on are some of the processes that can introduce risks in human spaceflight. For example, the risk of fainting if crew members, when crew members return to Earth and they're suddenly back in gravity. And this matters not so much on Earth, where we can take good care of them, but it matters a lot on Mars or on the Moon. If they suddenly get dizzy and they're going to pass out because their blood pressure is not well regulated because their blood volume's wrong. So we work across a lot of those things and develop what we call countermeasures to make sure that any of those unintended effects of the strangeness of the space environment, right? Because there's nothing about us that evolved for living in that environment. Making sure that we have solutions for each of those problems.
Thank you. We'll take our first question from the room.
Hi there. Thank you so much for this presentation. My understanding is that the International Space Station is set to retire pretty soon, and I'm wondering how some of the Earth monitoring systems on there will continue their missions and what the plans are for after it retires.
Yeah, so the International Space Station is slated to, it's really getting to the end of its life now, and it's slated to end in 2030. What we're doing with the instruments on the International Space Station is we're actually, now that we've proven those technologies, we're planning for key components of those to become part of the Earth System Observatory. We will also probably continue to test instruments on future commercial space platforms. So there won't be a big intergovernmental space platform, but there are a number of companies, such as Axiom, that have agreements and are proving out the ability to operate small commercial space stations in the future. So I think we'll continue to operate instruments on those platforms. At the same time, if I take EcoStress plus EMIT, that's what's going to be an SBG. So that is one of our next missions coming up.
Another one of our online viewers asked, any thoughts yet on the next generation of instruments that you would like to fly after those that are on the ISS?
Yeah, so one of the things that we do in our technology development is we look at different kinds of user needs. We look at what do we need to know better from our models, and then we also look at what other kinds of things are needed here on Earth. And one example is in fighting wildland fires. It would be really nice to be able to see places where fires are starting before they're detected today. And so we're working to advance thermal imaging so that those thermal imagers could either be used on aircraft or on satellites to help us do a better job of predicting and monitoring wildfires.
Mm-hmm. One of our online viewers says, I am in Detroit. Our snow melted as well this year, but last year it did not. We had snow almost all winter last year. So doesn't this indicate that there can be cycles not influenced by outside sources? And you showed some of those cycles in that loop.
Yeah, there are annual cycles. There are cycles driven by things like El Nino, La Nina. There are some times where the polar vortex is kind of sending all the snow our way. There are other times when it seems to be sending it more to Europe. And so it's really tricky because if you can't take the experience of one particular year all by itself. What you really need to do is look at the climatology, look at those patterns over time, which is why I showed you a number of graphs that were covering the entire period of human spaceflight observations where we know those things. And so it's really important, but even so, many of us are now recognizing that many of the most recent years were a lot warmer than those years we remember a long time ago. So you can still understand it instinctively, but as a scientist, the thing you really got to do is plot that data and be sure.
Yeah, well, those long-term trends are key.
Yeah.
We'll take the next question from the room.
Hi, yeah, I was just curious. As far as the satellites currently going around and the missions currently going around the Earth, what information do they track about natural disasters? And is that information useful for predicting them?
Yeah, that is a great question. So we do have a disasters program, and it's actually a collaboration of all the international agencies that fly satellites in space, and even the astronauts in the International Space Station get activated if we know there's a disaster and people could use information about that from space. They'll go to the window and even take a photograph if that's helpful. We do work to predict disasters where we can. So, in the areas of wildland fires, we're very interested in predicting where the fire risk is greatest in order to perhaps intervene and certainly to warn people. We also work on predicting hurricane strengthening. So we're getting ready to launch a mission of CubeSats this summer called Tropics. They're actually on their way being shipped to New Zealand for launch right now. And those Tropics CubeSats are going to get really detailed information about eye wall cycles and how those eye walls recycle. And that will help us to better predict this really disturbing thing. Any of you who've lived along a hurricane coast, like I spent years in Houston, right? We think we have a usual pattern, and all of a sudden in the last 10 years, we've seen these storms that are sort of category 2, category 1, nobody's worried about them too much, and then boom, category 5. And we really don't understand that pattern. That's a modern, last few years pattern. And a mission like Tropics is going to help us understand that better and perhaps, I hope, improve our hurricane predictions by understanding those eye wall replenishments. So those are a couple of examples.
24-hour cycles and just make an enormous difference in
Yeah.
the impact of a hurricane on the coast.
Oh, yeah.
Another question from our guest in the room.
Hi, thank you again for being here and presenting such great work. I was curious how often you collaborate with other federal research agencies, especially those that do the ground-based observations, especially when it comes to planning future missions.
Yeah, so we collaborate very closely. When we plan these future missions, we actually have science and applications teams that include representatives from some of the other government agencies. The Greenhouse Gas Center that you heard in the final video is a partnership that includes the EPA, the National Institute of Standards and Technologies, and NOAA. We all come together in a working group to talk about the best ways to solve this problem and bring each of our skills to that mix. And in fact, NASA builds the satellites for the USGS, for all the Landsat series, that then the USGS uses to understand and manage landscapes across the country. And we build the satellites that are operated by NOAA for weather. So we work very collaboratively to make sure that those satellites meet their needs as well.
And we're going to take 2 more questions here from our guests in the room.
Awesome. Thank you so much. This has been awesome. I'm curious about how NASA communicates the findings that the ISS measures to relevant stakeholders, whether that's like an oil company in Texas or, county firefighters.
Yeah, so what we've done with EMIT is really interesting because we have something now we call open data, which means as quickly as possible, we have a policy at NASA that all of our data goes public. And so with EMIT, we've been releasing data cubes as quickly as we can. So we've put out 5,000 data cubes so far, and it was on the cover of the Iran Times. One of our data cubes showed a methane leak from what looked like, we weren't really sure, but it looked like it might be a landfill based on sort of other imagery from the context. And they went, and the Iranians went and capped that landfill because they saw this information and they could act on it. So sometimes we can put the data out there. If we put it out there in a reasonably useful form and people can find it, they can use it.
Okay. And our last question from the room.
On the topic, and thank you very much for presenting, on the topic of EMIT, what's the resolution of EMIT? And also the cooperation of the utility companies when they know they have a leak? Do they report back to EMIT, and is that information then distributed, or is it very one-way street from EMIT to corporations?
So it's collaborative in that we have forms, and this is part of what we're doing with our Greenhouse Gas Center is building this up a little more formally. But we put the data out there. They can use it or not use it. It's not regulatory data in any form. But we are working with our EPA colleagues to see if they could use their government agency mission to structure things to take better advantage of the data than we do today. Then we also have the ability for those people that see something and property they care about and go out and find that to then come back and tell us if it worked or not. And then we're planning on doing some airborne flights this summer where there are certain situations where you'll have a methane leak of a known, because for some reason, there's going to be something that happens and there'll be a certain amount of methane that leaks. And so we're going to overfly those with the same instrument that we have on the space station so that we can validate those numbers so that the colors on that represented a flux, the amount of methane that it looked like was coming out. And we want to make sure that algorithm's really accurate. And that's one of the reasons we partner with NIST, the Institute of Standards and Technologies. So this is a work in progress. We're at science quality with the data or research quality with the data. It's not at a quality where we could say that somebody's absolutely doing something. What's been amazing to me is how many people have found this useful so quickly.
Thank you again very much for sharing your wisdom and experience with our audience here in the room and also with a much larger audience that's online and with anybody who may be watching this lecture in the recorded format in the future. Thank you very, very much. Our next lecture is May 3rd, Taking on Challenges with Intention, Making History with the Lockheed U-2. And the next lecture in the Exploring Space lecture series will be on May 24th, Exploring the Moon and Mars, Learning to Work and Live in Space. Outside, we're going to have stargazing available until about 10 o'clock. The weather is good, so if any of you in the room would like to go out and take part in that, please feel free. Thank you very much to Dr. Julie Robinson for being with us.
It's a pleasure.
I'd like to thank our sponsors again, Aerojet Rocketdyne and United Launch Alliance, for their support of this series, for making everything possible, and thanks to all of you for joining us here. I hope we'll see you again at the next Exploring Space lecture.